Good morning. Today we will discuss a topic called the finite differences, introduction to finite differences in the subject computational fluid dynamics for 6th semester mechanical engineering students. Myself, I am P. Venkata Mahesh, assistant professor in Department of Mechanical Engineering, Institute of Aeronautical Engineering. Now, the CFD is based on discretization. Okay, the subject CFD is based on discretization. Now it comes under the numerical solutions. Okay, we have two types of solutions. One is analytical solution, the other one is a numerical solution. The analytical solution, if you see, it will give the variation of the dependent variables throughout the domain. But if I see the numerical solution, what it will do, it will give the values at a discrete points in the domain. It will not be a continuous value. It will be at this particular, say suppose in this diagram you can see, you have discrete points and the solutions, the numerical solutions based on CFD or FEM or anything, they will be giving the values at the discrete points called grid points. Now we will see one discretization technique called FDM, finite difference. Before that we will see what is called the discretization. So suppose this space, okay, the space xy space is there and it is having a grid. The x direction uniformly it is divided by a value of delta x. So from here to here it is delta x, here to here it is delta x, like that it is divided. Similarly in y direction also it is divided in delta y, like that. But in general if you see, the delta x values may not be uniform in x direction and the delta y values may not be uniform in y direction. But what we will do in CFD is we will take these differences uniform, or we make them uniform so that our coding will be very simple. Now here in the discretization, say suppose this point is there. This is the point at which we are present. Okay, we are now at this point and this point is designated by ij. Okay, we are giving that point some index called I comma j. Now the index I is running in x direction and index j is running in y direction. You can see here the I here I, before it is I minus 1, after it is I plus 1. Now here in this, if you see in y direction, this is j, below it is I minus j minus 1 and above it is j plus 1. So the j is changing in y direction and I is changing in x direction. Now there are many discretization methods called FEM, FDM and FVM. Okay, now we will see what is FDM, the finite difference method. In this class we will discuss about the finite difference method because it is mostly used in CFD. Okay, in CFD, finite difference method and finite volume method are mostly used. Now we will discuss about the finite difference method. Now what is this finite difference method is all about? The finite difference method is nothing but replacing the partial differential terms with an algebraic difference terms. Okay, the partial derivative terms are replaced by algebraic difference terms. So that is called the finite difference method. Okay, and the finite difference method is based on the finite difference representations are based on the Taylor series expansions. Now, what is this Taylor series expansion? First, we will see what is Taylor series with an example. Why we are taking so many terms in Taylor series and all. With an example, we will see, and then we will go back to the finite difference method. Now, here f of x is a function of x which is continuous, okay, and all derivatives are defined at x, okay, all the derivatives of f of x are defined at x. Then the value of f at x plus delta x. So the value of f is known, and all the derivatives of f with respect to x are known at a point 1 or at a point x. Now what we are doing, we are finding the value of f at a location x plus delta x. So what is the distance between x, first point and second point? It is a delta x. Okay, the distance between the first point and second point is delta x. Now, this is what I am saying. We know the value of f at x or 0.1. What we are doing, we are finding the value of f at x plus delta x or 0.2. And for doing this, what we are using is the Taylor series expansion. So, what is this Taylor series expansion? F of x plus delta x is equal to f of x plus dou f by dou x into delta x plus dou square f by dou x square into delta x square by 2 factorial plus so on, and it will be dou n f by dou x power n into delta x power n by n factorial, so on. So it runs up to infinite number of terms. Okay, but why we have to use infinite number of terms? Okay, we'll see. Say suppose f of x plus delta x, we say it is equal to f of x. When it is possible? When they both are in one horizontal line. Okay, if they both are in one horizontal line, then f of x and f of x plus delta x may be same. But here it is a curve and it is not in a straight line. So the value will be different. Now what I am doing, I am taking a dou f by dou x into delta x. What it is doing? It is considering the slope from 1 to 4. Here at this point, it is taking what is the slope of the function f and then multiplying with delta x. So the value will go up to here. So this is also not correct. So what I have to do? I have to take the curvature into consideration. If I take the curvature into consideration, then it is dou square f by dou x square into delta x square by 2. Okay. Now if I do that, it will come to here. So the error is less. Okay. So if I add more terms, what happens? The error will be negligible. Okay. If I practically add infinite number of terms, then I will get the exact value at 0.2. But if I use infinite number of terms, it is not possible to calculate. So we'll cut off at that some point, and that is called the truncation error. We'll see that. Now we'll see one example here. F of x equal to sine 2 pi x. So this is the function. So the curve is defined by f of x equal to sine 2 pi x. Now at this point x is equal to 0.2 and at this point it is equal to 0.22. So what is delta x? Delta x is nothing but 0.02. So the delta x is known and f of x is known. Now the first term, if I consider only the first term in the Taylor series, and then it is equal to f of x. f of x plus delta x is equal to f of x. Then the exact value, if I see, the exact value is this, but f of x is this. So the error is 3%. There is a lot of error is there. Now if I add the slope term, what is happening? We know what is delta x is 0.02 and dou f by dou x. We need dou f by dou x. How to get the dou f by dou x? Differentiate this with respect to x. Then dou f by dou x is equal to 2 pi sine. It is cos 2 pi x. Cos 2 pi x. Okay, 2 pi cos 2 pi x into delta x. So if I substitute all the values in this, I will get this value. Now if I see the error, this is the exact value, but this is the value I am getting by considering the slope at point 1. Then the error percentage is less. It is reduced, but it is still significant, 0.7%. Now if I consider the curvature term also, so the curvature term is dou square f by dou x square. So the dou square f by dou x square means I have to differentiate it further. What I will get? 4 pi square minus sine 2 pi x. So this I will get. So if I substitute all these values here, what I am getting? I am getting the error to 0.01%. So if I add further, the error may become 0.0001. Later, if I add further, it will become 0.0001. Like that, it may reduce. The error may reduce. But depending on my requirement, I will end the solution at some particular point. Okay. Now we will come back to the finite difference method. So far we have seen what is the Taylor series expansion and what is the significance of having the infinite number of terms. If I have infinite number of terms, I will get exactly mathematically exact solution. But infinite number of terms is not possible. Then what I have to do? I have to truncate it, or what I can do? I can reduce the delta x. I can take very small, very negligible delta x term. So that is also having a disadvantage. Say suppose I am having a value at this point. At this point, very small value I have to calculate. Like that I have to calculate. Then I will get infinite number of points. If the difference is infinitely small, then I will get a infinite number of points at which I have to calculate. Then again the calculation will take a long time. Okay. So this is also not possible. The delta x tending to 0 is also not possible. So what we have to do? We have to take the delta x as small as possible and the terms, the maximum the capability of the system, that many terms I have to take in the Taylor series. Now we do something called truncation. Okay, what I said, I can take the number of terms based upon the mathematical or the calculation capability that we have. The system, if I have a very big system, I can take 10 terms or 20 terms. If I have a small system, the speed is very small, then I can take only few terms in the Taylor series. So that process is called a truncation of this expression. Now in terms of magnitude, for example, higher order terms are neglected. Okay, delta x power cube and higher order terms are neglected in the Taylor series, then this equation is obtained. Now delta x cube terms are neglected, so the equation is second order accurate. Okay, the equation is accurate up to second order. Say suppose the first order is this, then the second order is this. Okay, the third order may be this. So if I neglect this term, the accuracy that I will get by this equation is only second order. So if I neglect this term also, okay, we neglected this term, the third order term we neglected, we got the second order accuracy. Now if I neglect the second order term, I will get the first order accuracy. So this is called the first order accurate equation. Now what is the term that what is the term called, what is the name given to the term which is neglected? So if I neglect up to here, or if I truncate up to this equation, the truncated portion is called the truncation error. Okay, the terms that are neglected, they are called the truncation error, and they can be represented like this. So this is the second order accuracy. I am getting second order accuracy, so the third order terms are neglected. If I am getting the first order accuracy, I am neglecting the second order terms in the Taylor series. So this is the designation that we are giving for the truncation error. So the requirement is to minimize the truncation error or to increase the accuracy. Either you have to reduce the truncation error, or the other words you can say the same thing as increasing the accuracy. So how to reduce the error or increase the accuracy? By reducing the delta x or taking the higher order terms as many as possible. So okay, the same thing we are doing here. We are seeing in a different direction. So this is the equation that we are dealing with, the Taylor series, and if I bring this fellow, okay, if I bring this fellow this side, okay, and all the other terms this side, and I keep this term, the partial differential term, on one side. So what will happen? That will become like this. So this is the finite difference, okay, the finite difference equivalent. This is the finite difference term for first order differentiation of the x of u with respect to x. So the first order partial differential equation we are getting like this. Okay, this is the finite difference term. Now what is this? What we are doing here? We are at this particular point ij, and we have considered the point ahead of it. So it is called forward finite difference. Now the truncated term is represented as order of accuracy delta x, because the delta x terms are neglected. So the order of delta x accuracy we are getting. Now what is this? This is order of accuracy of delta x, so that we have discussed. Now the order of magnitude of the truncation error is explicitly by O notation. So instead of writing any other term, we are writing the order of accuracy or the truncation error in the form of O bracket. What is the order we started neglecting from? So the order from which we are neglecting is delta x. Okay. Now this partial differential term is expressed in terms of finite differences. How we have done? We have moved forward in space, so it is called the forward difference. Since we have moved forward in the space, it is called the forward difference, and the order of accuracy is first order, so it is called first order. So this is called the first order forward difference of the dou u by dou x. So the first order forward difference equivalent of the partial differentiation of u with respect to x is given by this. So how to get the backward difference? So suppose if I am expressing the Taylor series for I minus 1j, previously I have expressed the Taylor series for ui plus 1j. Now what I am doing, I am expressing the Taylor series for ui minus 1j. So how to write that? We don't have to remember this series separately. Here I minus 1 is there. So previously it was ui plus 1 j. Now here it is ui minus 1 j. So how can I write this? Ui plus minus 1 j. Like that I can write. So in place of 1 I have to put minus 1. So here delta x, in place of delta x I have to put minus delta x square minus delta x cube. Like that if I put in the previous Taylor series, I will get the Taylor series for ui minus 1 j. So if I simplify this one is having power 1, so I will get a negative 1. Here the power is 2, so I will get a positive term. Here the power is 3, I will get a negative term here. Now if I bring all these terms this side, I am keeping this one on one side, all the remaining terms on the other side. If I bring, what I will get uij, okay, uij. This will go this side and this will come this side. So it will be ui minus 1j. uij minus ui minus 1j. uij minus ui minus 1j by delta x. This is delta x and the remaining terms is order of accuracy 1. So it is a first order accuracy but backward difference. So previously it is a forward difference and this is a backward difference. Okay, that is the difference. So we are moving in backward direction. That's why it is called backward difference. We are moving from this point we are moving this side, it is forward difference. If I am moving from this side to this side, it is a backward difference. Similarly, I can write for the y also. If I am moving in the upward direction, it is positive. If I am moving back downward direction, it is a backward difference. This is forward difference in y direction and this is the backward difference in the y direction. Now we will see something called central difference. So we are at this point and we are using this point for one point ahead and 1 point behind and finding the partial differential term. So how to do that? We have two equations of Taylor series. One is ui plus 1 j. The other equation is ui minus 1 j. These two equations, if I am subtracting this one from this, what I will get? This will get eliminated. This term also will get eliminated. Like that, all the positive terms in the backward ui minus 1j, all the positive terms in the ui minus 1j will get eliminated and I will end up with the negative terms. And then because this minus this means this negative will become positive. Now what I am doing, if I simplify this equation, I will get ui plus 1j, ui minus 1j is equal to 2 into dou u by dou x ij into delta x. This delta x is there. Now in the third term I will get dou cube u by dou x cube ij delta x cube by delta 3 factorial. Like that I will get. Okay, so here it is 3 factorial and 3 factorial into 2. Here I will have 2 and here I will have 2. The 2 will get cancelled and I will remain with 3. So like this I will get. Now what I have to do? I need only this. I need only dou u by dou x. So the dou u by dou x, I have to keep one side. I have to bring all the other terms this side. Then I will get this equation. So this is called the, what is the order of accuracy here? it is a delta x. If I divide this here, it will be delta x square. Okay, here delta x cube is there, here delta x is there. If I divide this, I will get delta x square. So the order of accuracy increased here. The order of accuracy is delta x square. Previously, it is only delta x. So here the order of accuracy is delta x square. Now, this second order, since it is order of accuracy is 2, it is called a second order. Now, what type of difference we are taking? We are at this point, we have taken the one step forward and one step backward, and it is called the central difference. Second order central difference. So, if I want the partial difference and the finite difference for dou square u by dou x square, how to get it? If I add these two, previously I subtracted this from this. Now what I am doing, I am adding these two. If I add these two, all the negative terms will go. All the negative terms will go, and I will end up with this equation. So what is this equation? Ui plus 1 j plus ui minus 1 j is equal to 2 uij plus 2 dou square u by dou x square delta x square divided by 2 will be there. Here 2 will be there. These two will get cancelled, and like this I will get some equation. Now what I want dou square u by dou x square. I keep this one side and bring all the other terms this side. What I will get now? Here delta x square is there, here delta x power 4 is there. If I differentiate, if I cancel this, I will get order of accuracy as 2. Previously also the central difference we got order of accuracy 2. Here also the central second difference. This is a central second difference. Why we are saying central second difference? Difference between these two and difference between these two, both are there here. So if I use difference between these two and difference between these two, it becomes the second difference. Since we have two differences, we are dividing with the delta x square. So it is called second order. Why second order? Because the order of accuracy is delta x square. So it is second order. We are at this point and we are using forward and backward two nodes. So it is called central, and we are finding for the second derivative. So it is called a second difference. So it is second order central second difference. Now we will see the mixed term. So far we have seen only one term. So if I have a mixed term like dou square u by dou x dou y, how to find the finite difference for that? So these are the two equations that we are having from the beginning. What I am doing, I am differentiating these two equations with respect to y. So if I differentiate this with respect to y, it is dou u by dou y. And similarly, if I differentiate this with respect to y, I will get dou u by dou y. And here also dou u by dou y, dou u by dou y. Here dou square u by dou x dou y. Here dou square u by dou x dou y. Here dou cube u by dou x square y. Here dou cube u by dou x square y, like that we will get. So from that we are getting these two equations. Now in this equation, what I am doing, I am subtracting this. Okay, I am subtracting this from this equation. If I subtract like that, these elements will go, these elements will go, all the negative elements will be remaining. Then what is this? It is dou u by dou y I plus 1 j minus dou u by dou y I minus 1 j is equal to 2 into dou square u by dou x dou y. Okay, this one 2 into dou square u by dou x dou y into delta x, and here I will get 2 into dou power 4 u by dou x cube dou y into delta x cube by 3 factorial. Like this I will get further equations. Now what I want only is this. So if I divide this with this, if I divide this with this, I will get order of accuracy delta x square. Now, and what I am doing, I am dividing this 2x this side, so it will become like this. Now I have dou u by dou y and dou u by dou y here. So if I substitute those values of dou u by dou y and dou u by dou y, I will get what is the finite difference for this equation. Now, what is the dou u by dou y? So dou u by dou y, it is the forward difference, and it is the backward difference. So forward difference in terms of j, and here also the forward difference in terms of j. The I plus 1 is common here, I plus 1 is common, and sorry, it is central difference. Sorry, this central difference I am taking. If I am taking central difference, it is dou u by dou y, I plus 1 is common, and j plus 1, j minus 1 divided by 2 delta y, and here also I minus 1 is common, j plus 1, j minus 1 I will get, and 2 delta y I will get, and if I simplify this, I will get this equation. So this is what is the order of accuracy here? Delta x square and delta y square. So it is a fourth order accurate function. The fourth order central in x and y. Okay, this is the fourth order central x and y. So in this way, you can find out the finite difference equivalent for any partial differential term. So in this, to summarize, in this class what we have done, we have seen what do you mean by discretization, and in that what is the finite difference. So in finite difference, what we are doing, we are taking two nodes and the partial differential term is replaced by the finite differences, that is called and making it into a quadratic equation. Okay, now the finite difference replacement is also done in three different ways. One is forward difference, one is backward difference, and the third one is central difference. So you can use forward difference, backward difference, and central difference and formulate the finite difference terms for any partial differential term, okay, in the governing equations. And we will see further in next class. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.